windy. And Alondra, just in the nick of time. Okay. We will start with that. Good afternoon, everybody. Oh my gosh, we got a full class today. Wow, these double color days. It's almost like a Friday, but I'm here, and so it's as if it's a real class with the whole group here. Almost the whole group, most of the group, right? Okay, and we even got one more because Amy's coming in today instead of tomorrow, which actually is going to be a huge benefit because today's the day I'm actually going over stuff. Tomorrow we're just going to work on problems independent time, so you're not missing anything from there. Speaking of which, right, we just read a new section this weekend. That section gave us 3 new strategies, problem-solving strategies that we can use to solve problems, and so I want to go through some examples, more examples than just what you had in the book, of using those strategies live and in person, and I've got some extra tips and tricks, things to consider to throw in there along with them. And then at the end of the period, we'll have our reading quiz about those 3 strategies. And from there, you can get started on your new problem set for this week, which, as alluded to just earlier, you will be working on tomorrow in class time, and then it will be due on Friday. Okay, so you got the whole week to tackle those problems. So that said then, let me click a few buttons here, make sure that's going there, and let's get started. So those new strategies are simplifying the case. What? Who? What happened?
And then I stopped.
Something there. I don't mind you chiming in for an actual question. But please keep muted if you're just going to have chat over the airwaves, okay? Anyways, so our 3 new strategies, simplifying the case. And I moved this one to the top because I think it's probably the most powerful one. Second only to drawing a picture. This is possibly the most useful thing you can have in your toolbox in any situation, applied to life in general, right? If you can make things simpler first, it's going to make everything so much easier. Second, we're going to get organized with creating a table. And that's really going to go hand in hand with our 3rd strategy, finding a pattern. For a lot of people, it's much easier to find said pattern when everything is sorted in a table format. So let's put those to use. Our first problem. We are to find the number of toothpicks required to form each of the following patterns, and then predict the number of toothpicks needed to form the nth pattern. Well, already I'm picking up. It said patterns, nth pattern. It's got the word pattern in it, okay? If you can't figure out that you need to use the find a pattern strategy for this one, you need to go back to 2nd grade and learn some basic vocabulary all over again, okay? It's got the word right there. Specifically, what are we looking for? We're looking for a number of toothpicks. Okay, so this is another toothpick building puzzle. You could get some actual toothpicks if you're a hands-on kind of person and start manipulating these. We're just going to stick with drawing. And because I keep having to erase my work between classes, I also erase this edit here. I did not get the diagram properly copied. I do apologize. This is not part of solving the problem. That's part of the setup. There's supposed to be another one right there on the end. Okay, so now that I have fixed that, let's now solve this pattern. What's going on with these toothpicks? What do we understand from looking at this? I hope we can recognize that shape. There's a hexagon. In fact, now this is 2 hexagons. This looks like 1, 2, 3 hexagons chained together. So what do we know about hexagons? Right? 6 sides, 6, 12, 18. Start thinking of multiples of 6. That might come in handy. What do we know about chaining the shapes together? Notice the lack of any toothpicks in between them, right? They skip all that. You get one outline of the whole thing. Have we seen anything like this before? We have. We did a problem like this, except with squares, right? It was one square and then two, and then squares all in a row. How many toothpicks for the squares? So it might help if we could remember our experience from that. Hey, what strategies, what formulas, what worked from that problem that we could apply to here? If you don't remember any of that, that's okay. We'll start from scratch. But all of that experience helps shorten the deal, right? Let's see. If we are looking for the number of toothpicks, I think we ought to start counting. And if we're going to be counting things, I think a table is going to be really nice to help organize that information. I would like to always simplify whenever possible, but they've already done that for us, right? They've given us the simplest possible version. They didn't start us out with 17 hexagons in a row, right? They started out with one. So they already did the simple part. So we're not going to implement that one on our own, but keep that in mind that they've already given us the basic set. Always check for that. Is this the smallest version I can get? Start from there. So let's start a table here. We'll go with number of hexagons versus number of toothpicks. So for one hexagon, we used up one toothpick per side. So that's going to be 6 total toothpicks. For 2 hexagons, you would think 12. If they were separated, it would be, right? 6 for each one, except they share this side, and that doesn't get a toothpick. So really, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 toothpicks. So 2 hexes in a row needs 10 toothpicks. And for 3 hexes in a row, let's count. 1, 2, 3, 4, 5, 6, 8, 10, 12, 13, 14. 14 toothpicks. So far, all we've done is just recorded what we already know in a different format. Did that give us the answer? No, right? So we ran one strategy. We created a table. Did that give us an answer? Step 4, reflect. How did that go? Well, it gave us a better understanding. Now we've got a new way to look at things. So let's go back. Next strategy, find the pattern from here. If you're a very visual person, maybe you would find the pattern just based on that. If you're a very numbers person, maybe you like this version better. We can probably see, you've probably done this a lot in algebra, right? Find the difference in the table. From 6 to 10, that's plus 4 toothpicks. From 10 to 14, that's plus 4 more toothpicks. Hey, I got the same thing both times. That's a good thing. That's a good sign. That leads me to believe that that's the pattern. That's probably it. I just need to keep adding 4 toothpicks every time. Let's make a prediction. Let's test that theory. We'll go a little scientific method here. If I was to add 4 more toothpicks, I would end up with 14 plus 4 is 18. Does 4 hexes take 18 toothpicks? Let's put it to the test, shall we? If I want to draw 4 hexes, let's put the side there. We have the top, and then the top, and then the top, and then 4 tops, right? The pointy bits. And the other side, and then we have 1, 2, 3, 4 pointy bits on the bottom. So altogether I had 1, 2, 3, 4, 5, 6, 7, 8 pointy bits. So 2 times 8, that's 16, 17, 18. Add in our ends. Yes, that's what we got. We wanted 18, we got 18. That works. I have verified. I tested, I found a pattern, I checked that pattern, I drew a picture to help verify that pattern. And now I'm like fully convinced that yes, this is in fact the pattern of toothpicks. The only thing I need now is in terms of n, right? The nth bit. So how do I do that? How do I turn it into an nth formula, right? For every hexagon you need hexagon n number of hexagons. I need so many toothpicks. So you got to go from directly from one to the other. Instead of the differences, now how to go from 2 to 10, from 3 to 14. Now you can find this out based on the differences. You can make use of that 4. It's going to come into play, right? I had to add 4 each time, so I'm going to have 4 times as many hexes. You could also go based on the way I counted these, right? If you're a very visual person, look at that picture. How did I shorthand? I needed to draw this real quick. So in my mind, I simplified this as, oh, it's just 2 on top each time. 2 on top for each hex. So per hex, that was 2 times n, right? And then there was another 2 for each hex on the bottom. And then the 2 sides, right? So just 2 extra to go on the ends. Add that all together. So all of my hexes give me a total of 4 times n plus 2 extra. All right? And again, you could look at, how do I go from 4 times as many, from 2 to 10? Well, 2 times 4 is 8, add 2 more. 3 times 4 is 12, add 2 more to 14, right? So a couple different ways you could get to that. Let's reflect on this again. This was similar to the squares in a row. Now we did hexagons in a row. Could we do other shapes in a row? Is this always going to be a system that we could use? Just make a table, find the pattern, done. Is it always going to be a linear relationship? Will we always find that first difference there? Questions to consider. What other shapes are possible? We could do octagons. I think octagons would work out pretty nicely. Right? And then you could stick another one onto the side there, except you'd have to erase the middle one. Right? Those would fit up. Pentagons, though, pentagons would screw the whole thing up. Right? Because then it starts to get kind of crooked here. Right? It starts to bend around instead of making a nice straight row. Because they don't have these nice parallel sides to them. Okay, so there's some limitations on the types of shapes we could expect to use here. Does that have a practical implication? Maybe. I don't know. My first thought is tiles. If you are like tiling your bathroom floor or the kitchen backsplash or something, there's a reason why the store doesn't have any pentagonal tiles, okay? Because they don't form nice, neat rows. All right, something to consider. Any questions from you guys on the toothpick problem? All right, let's go to the next one. The hexagonal numbers. Hexagonal numbers. What are these, like shape numbers? Are whole numbers that represent the following shapes. Yeah, they literally created a set of numbers because you can make shapes with those numbers in them. So you make hexes out of dots, you get the hexagonal numbers. That reminds me, we did a problem with the triangular numbers, and I think there was an example in the book that did the rectangular numbers as well. So we've already seen this twice. So you could draw on that experience. Remember, triangular numbers looked like this. We started with 1, then you had 3, right? Dots make a triangle. Then it was 6, because you added a row to the triangle. You keep the same and you just add another row to it. Except in this case, it looks like visually, here's a hexagon, here's the same small hexagon. Instead of just another row, we're adding like another layer of hexagon. This is the hexagon onion here. All right, so that's a little reminder there. Again, I've given the smallest possible case. They've already simplified it for us. We are finding the number of dots in the nth hexagonal number. So I need to find the pattern. That is explicitly what the problem is asking for, is the pattern, the formula itself. So I got to get that. I'd say this setup worked pretty well. They're like, here's a few pictures. I'm going to make a table, find the pattern that way numerically. Might have to draw an extra one as we go, but that system worked fairly well. Let's apply it here. So we'll start with a table of what we already know. For the hex number and the number of dots. To make that, the first so-called hexagon was only 1 dot. Okay, you got to start somewhere. Hex number 2 is the actual hexagon here. Is there a way to interpret that actual number 2 from this? Yes, there is. And that would be the number of dots on a side. Okay? This looks like a single length. This is the fence post problem. The difference between the posts versus the fence is in between the posts. Right? 2 is the number of posts on a side of the hex, not the number of segments of the hex. Just like 3 here. 1, 2, 3 dots, not 2 segments. Okay? If you had to measure the length, it would be 2 units long, but 3 posts worth. All right, so we're numbering our hexes based on dots per side. So we get 6 total dots to make the full hexagon there. And then here we keep that same 6, and then we added 1, 2, 3, 4, 5, 6, 7, 8, 9. We added 9 more. So for the third hex, we added 9 more, so that's 15. Okay, so I've already got my, working on my first difference there. I added 9. Let's go back. From 1 to 6, that added 5. Shoot. It's not the same thing. This is not as easy as the last one, unfortunately. It's going to take more work. And I don't already have an immediately obvious pattern there. It's not the same number. 5 to 9 could be anything, really. Okay? Let's go one more. All right? When in doubt, draw another picture, gather more data. Let's draw one more. Let's make the 4-side, or 4 dots per side hexagon. I'm going to take this. It's already drawn for me. Stretch it out to 4. And then we got to go 2, 3, 4 dots on that side. 2, 3, 4 dots there. 2, 3, 4 dots there. Make those nice big dots so you can see them. And 2, 3, 4 dots there, and connect to get 1, 2, 3, 4 dots there. Okay. It's a little sloppy. That's okay. I'm not trying to draw the perfect picture. I don't have hexagonal graph paper to guide me. I just need to count the number of dots. All right? So if I'm concerned about number of dots per side, as long as I keep that consistent, 1, 2, 3, 4, 5, 6, yeah, I got all 6 sides. Okay. It meets all the parameters. Now we count. How many did I add here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Plus 13. And since we're looking for their total, we got to keep track of that too. It'll be 28 for the 4th hex. 28 dots. We added 13 more. Well, that's something. 5 to 9 to 13. What's the pattern there? Maybe there's a second difference. To 5 to 9 is plus 4. From 9 to 13. Ooh, that's also plus 4. Hey, how about that? So this has the second difference so far is constant. And coincidentally, it's also plus 4 again. I don't know if that's because it's still hexagons. Could be. Something to investigate for later. So our prediction, we think that this ought to be plus 4, which would mean that would be plus 17 more. Right? So 28 plus 17 would be 30, 45. Or a 5 hex. That's our prediction. We're not sure yet. We have to test it, just like we did with the toothpicks. Okay? Because 2 data points is not enough to be sure of the pattern. Let me reiterate that. 2 data points is not enough to be sure of the pattern. Let me give you a real obvious visual here. If I gave you some like real-world data, okay, said this was the first point, and then the next one was here. And I said, hey, make a prediction. Where is it going to go next? The simplest answer would be a straight line, right? But that's not always the case. What if it was some kind of a curve coming through here? If you only have the 2 points, 2 points could fit on any kind of curve. You have no idea what it could be. If this is like your expenses in a business, right? If you budget for the blue line, but they end up at the red line, right? Out here, you're going to be in big trouble, okay? You grossly under-budgeted, grossly underestimated. Oh, gosh, right? Problem ensues. So 2 points is never enough. You need at least 3 just to tell, like, okay, what kind of degree of scale am I dealing with here? Is it linear? Is it quadratic, exponential, something, right? You need at least 3. So we've got to test this, which means the best way to test it is to build it. We're going to draw the thing again. Let's go one more layer. How many will we add for a 5 dots per side hexagon? I don't feel like drawing. That's a lot of dots. Can I like simplify my drawing somehow? I know I have to end there, and I know I have to have 5 along the side. So between the 2 endpoints, 5 minus the 2, that would be 3, right? So there should be 3 dots in the middle there. Do you agree with that? Do I need to like draw 3 individual dots each time? Dot there plus 3 more, and then here a dot plus 3 more, and then over here a dot and plus 3 more, and then connect. That's all my dots accounted for, right? I think we can do that. 3, 6, 9, 12, 13, 14, 15, 16, 17. I added 17 dots for that layer. That's exactly as I predicted. It works. The second difference is a constant plus 4. Good news, I have found my pattern. Ah, yes, I could successfully carry this out as many iterations as I need to and be confident that it is correct. Now the question is, how do we get to that nth bit? What's the general formula? How do I go from 5 straight to 45? How do I go from 4 straight to 28? How do I go from 3 straight to 15? Okay, 2 to 6. Always start with the simplest ones. Go down, well, 1 to 1. 1 to 1, it could be almost anything. That's almost too simple. Let's go 2 to 6. How do you go from 2 to 6? This second difference is a clue here. If you remember from algebra, second difference, that's a geometric series. That's going to be a multiplication relationship, not an add. I don't add the same thing, but I can multiply. So how do I multiply from 2 to 6? No, I'll stick with purple, right? 2 times 3 equals 6, right? Ooh, is it going to be just multiplied by the same thing? 3 times 3? No, that's 9. 3 times 5 to get 15, right? And then it would be 4 times 7 to get 28. Okay, so I have my n here. I have my dots over here. What do I need to multiply n by? Well, it's changing every time. So now I have to find a pattern within my pattern. Oh, we start all over again. Unless you already know a little something. If you recognize this right away, hey, 3, 5, 7, I know those numbers. Those are just the odd integers, right? 1, 3, 5, 7, 9, 11. There's every other number, right? The odd numbers. If you already know the general formula for the odd numbers, you've saved yourself some time. Oh, we'll just bring that one in. I know that one. How to generate odd numbers. The first odd number, 1, then 3, then 5. Odd numbers are 2n minus 1. So test that out. You plug in 1 here. 2 times 1 is 2, minus 1 is 1. You plug in 2, the second odd number. 2 times 2 is 4, minus 1 is 3. The second odd number is 3. Okay? So if you already know this little formula, we can use it right here as necessary. Maybe we need to adjust it. Is this the second odd number? It looks like that will work straight off our value of n. N is 2. 2 times 4 minus 1 is 3. Perfect. If not, if you don't already know that, you don't have this in your memory bank already, that's fine. It just means you have a new pattern you need to first discover the formula for. You have found, right? Talk about simplifying the problem. You found a smaller problem within your problem that you need to solve first. Right? The difference is experience with not just problem solving, but with arithmetic, with algebra, with geometry, rules and formulas and relationships. The more of that you have already stored away and remember, the quicker and easier some of these are, because you can just draw those out and be like, oh yeah, this. All of a sudden, all those facts and things you know become shortcuts for your problem solving. You don't have to start everything from scratch. But if you don't know them, you can still just keep iterating on these strategies and work it out eventually, right, from baser principles. Okay, for the sake of time, I'm going to pretend we do know this, 2n minus 1. So then this guy, 2n minus 1, I need to multiply that by my n value there to get my number of dots. So we'll go ahead and distribute that. N times 2n is 2n squared. N times negative 1 is negative n. So there is the final form of my general formula for the number of dots in the nth hexagonal number. Right? So this will generate the sequence of the hexagonal numbers. Questions on that? Okay, one more here. 6 cities, A, B, C, D, E, and F, are located as shown next. Right down here. Hey, look, it's a hexagon again. If bike paths were constructed so that each pair of cities, that sounds important, pair of cities, be connected by a direct path, how many paths will be required? How many paths for 6 cities? I don't see the nth term written somewhere. So I don't need the general formula here. That might be good news for some people. Maybe the easiest path is to just find the general formula and then just plug in 6. Okay, that could be the case. I don't know. 6 is one of those where it's like low enough that if you found the pattern, 1, 2, 3, 4, 5, 6, maybe you could just do it by hand. We'll just go the long way. Won't actually be that long. I know, some things to keep in mind here. And again, with experience, you can be a better judge of what's going to be the fastest method, but all of them would work. I want to get a little more understanding here. I'm going to draw a quick picture first, just to make sure I know what we're talking about. Bike paths constructed, each pair of cities. So like between the pair of cities, A, B, we have one bike path, right? We don't need to go like from one to the other. It's not like a double-sided highway. It's just one connection. Okay, and in fact, let's go like simplest case. Let's consider the simplest case is 2 cities. Let's go one more. What if it was 3 cities? And then A to C, and then I think we just make a triangle, right? There's no other connections there. That's every city connected to all the other cities. So I'm drawing a couple pictures to try to get a better understanding here. I've reduced the number of cities to get a simpler problem. I think we might want to keep track of this. This is probably a good idea. Let's set up another table with our number of cities and the number of paths. And we'll keep track of this. We'll stick with black. 2 cities gave us 1 path. 3 cities gave us 3 paths. And we'll just find out this pattern until we get to 6 cities unless you find something shorter than that. Right? Here's one shortcut. Does this remind you of a problem that you've already done? We have so many things and you're just counting the connections, all possible connections between a group. Sounds like the handshake problem, right? Especially if you look at that diagram there. Okay, forget about the fact that these are cities instead of people, right? It's just one connection between each thing. That's like the total number of handshakes at a party where every person shakes every other person's hand. That was one of the example problems from the textbook, from the section that we just read. So if you recognize that and be like, oh, this is the same thing going on, apply it away. Maybe you just take that formula you found there, apply it here. Maybe you already had 6 people, and so you can like check, maybe you already had a table from that exam and be like, where was 6 people handshakes? Boom, there's your answer. Okay? It is perfectly acceptable in any problem you do to cite a prior problem and say like, hey, I know the answer for this problem because it's just like this other problem except insert, whatever difference, that, the coat of paint in this case, right? Just the aesthetics here. The numbers and the relationships involved are all exactly the same. Or maybe this is the same as that problem, but instead of 10, we're dealing with 20, so I doubled the recipe, right? Something like that. If you don't recognize that, then let's keep going. What about 4 cities in our network? How many bike paths do we need now? Well, A, B, C are already connected. We just need to hook up city D, right? So that needs to connect to all the prior cities. And it certainly seems at this point that like each new city we add just needs to connect to all the old cities. So we'll just add back in the number of cities we had before. So for 4 cities, we add in the prior number 3, so to the old total. So 3 plus 3 is back to 6. Ooh, wait. Oh, 1, 3, 6. Okay, if you didn't remember the handshake problem, perhaps you recognize the sequence of numbers. And this table really brought that to light. You're like, hey, 1, 3, 6, I've seen that pattern before. I know those numbers. Right? Some people might get excited and be like, ooh, 1, 6, 15, I know those numbers. I don't know the hexagonal numbers on site, but I do know the triangular numbers on site. 1, 3, 6, that's the triangular numbers. I bet this is just the triangular numbers. There's another shortcut. As soon as you recognize that, you have that glimmer of experience, be like, hey, there's a thing I already know. Connect it back. Use that. If you don't, then we just got to go the long way. We got to find the pattern ourselves. From 1 to 3 is plus 2. From 3 to 6 is plus 3. I bet we can see now this is, that's a constant difference. Second difference plus 1, right? Carry that on through. We're going to add 4 next time, which we justified it by adding, for the next city, add the prior number of cities. So for 5 cities, we'll add 4. That's exactly what we said here, right? 6 plus 4 is 10. Again, we could count. I could have counted from the very beginning, right? I haven't quite answered it yet, but I'm already thinking of other solutions. Hey, wait, could I have done it this way? Because it only takes you half a second to consider another possibility. Like, wait. That other way might be faster. Why don't I just, sometimes switching mid-track and finishing another way to get it done faster, that can work. But you have to get that experience first to know what's faster. At this point, I already did cities 5. I'm not going to try drawing more out. I'm pretty confident with this pattern here, since my experience from the handshakes, my knowledge of triangular numbers. I'm just going to go to 6. It's only 1 more. I don't need the general formula. Just go up 1 more. I added 4 last time. Let's add 5 this time. 10 plus 5 is 15. There's my answer. I'm done. Now, would I always leave it there? Maybe. Depends on the circumstance, right? If you're the county civil engineer, right? And your boss tells you, hey, we need you to count up possible bike paths. We're going to install a bike path network through the county, right? How many paths do we have to deal with? We're like, okay, we got 6 cities. There's 15 paths, all done. And then your boss comes back next week and say, hey, you forgot about a little township G over here that has a population of 15. They kind of want to be included too. And you're like, oh, man, one more, right? How far back do you go and redo all your work? Right? As little as possible, right? You don't have to redo all this and be like, oh, well, okay. If it's just one more city, maybe you just go one more on the table. But I would recommend, if the question only asks for one answer the first time, the next time you come across the same question, go ahead and get the general formula, if you don't already. Right? Even though I'm only adding one more, what happens if he comes in next week? What happens if this takes off like hotcakes and everybody goes, yes, we love county-wide networks of bike paths. The next county over wants to do the same thing. And then we're going to connect the inter-county bike path network. You're like, oh my gosh, suddenly there's way more cities, right? And then just go 8, 9, 10. Shoot, where's that general formula? Because now I need 20 and 50 cities all at once, right? So save yourself the headache and be like, as soon as it comes up the second time, just get the general formula and you future-proofed yourself, right? That's the formula for triangular numbers. We've seen that in other problems. I'll let you dig that one out. But this is why it's important to have good notes, so you don't have to do it all over again. All right. Final questions on the 6 cities problem. No? All right, then. If you could please take out your notes and turn your Chromebook's attention to quizzes. We've got our reading quiz to do in the next 9 minutes. Luckily, there's only 9 questions. Plenty of time. So go to joinmyquiz.com. Enter the game code 744155. Show me how much you know and can recognize these new problem-solving strategies. Such a loud popping sound. Oh, that's populating fast. Excellent. All right. Now, as usual, the retake code will be posted on Google Classroom at the end of the class day. You can use that retake code all week to improve your score. But I would like to get some data now. Had your hand up. Question? Yeah. Yes, you can use your notes. That's what notes are for. 744155. If you're in, go ahead and get started. Let's not waste time. It is still open. Okay. Show me as much as you can do here and now. And when you are done, go ahead and crack open the problem set. It's posted today. Do get started. Read through them today. We'll use class time tomorrow to actually work on them in depth. Okay? That will do it for the YouTube stream.